This is the final demo for the power subsystem for Team 11. I'm going to walk through how the subsystem works, how it ideally would work and interacts in different scenarios, and also talk about the features and how much we actually were able to get implemented under the new circumstances going around, obviously, in today's world. So first, just to talk about ideally how and kind of top level how this subsystem works. The subsystem essentially works by taking an input power from the wall, converting it to a usable power for our microcontrollers, as well as sensors and flow control systems to power the patient room control box. In the patient room, there's also a battery backup. That battery backup is to serve the purpose of, if the power goes out for any reason, the battery can then take over reliably and continue to power the IV system in the event of power failure, or in the case where a patient needs to be moved to another room. Ideally also, this circuit functions as a proof of concept for also just a straight conversion power subsystem for the nurse's control room. Obviously, basically, it would look the exact same just without the battery backups. So it actually interacts with every subsystem, which is really awesome. And it does so by providing a 5-volt theoretical power line and a 3.3-volt theoretical power line. So I'm using a 12-volt DC adapter at 1 amp to power this buck converter here. This buck converter is stepping down that 12-volt at 1 amp to a 5-volt signal at 1 amp. So basically, the buck converter takes that 5-volt signal, puts it into one input of this power mux. Path B is also running in parallel to that other path A. 5 volts is going into this eval module, which is then charging the battery, which is then discharging. In the case that the battery were connected across a load, it would be discharging across this boost converter, because as the Orbitronic 3400 milliamp hour battery only outputs 3.7 to 4.2 volts, which is obviously not a voltage that we could use for a 5-volt system. So basically, we have to boost it up and also bring it back into this power mux, where basically it's set in a comparison mode right now. So basically, if the wall power is off, so this right here, it will switch over to the second input right here, which is the battery. Else, if not, it will only ever use the wall input. It's outputting right now, as you can see on the screen, 4.357 volts across a theoretical load here. This theoretical load is set to 5 ohms. Obviously, if it was a 5-volt signal and we need 1 amp out of it, which is basically around the higher end of a calculated load that I came to, it could power that. So now you can see that when the battery is disconnected, the wall is powering the system. And now in the case where the wall is disconnected, you can see that the battery is still powering the system, which is great. That's exactly what we wanted to see. So now you can see the charging current actually working to charge this battery. It functions exactly as we needed it to.
This is the Nurses Station subsystem. It acts as a central hub for our sensing network and collects and stores the data before displaying it on a screen. In the event of an emergency condition, it makes an audible alarm and turns on an LED to indicate that there has been an issue in one of the patient rooms, which we will now demonstrate. This is the alarm to let the nurse know that a fluid level is getting low and will need to be refilled soon. And this is the alarm to let the nurse know that the fluid level has gotten dangerously low and needs to be refilled immediately. The device is able to monitor multiple rooms at a time. The nurse's station only directly interacts with 2 other subsystems. It receives a power input from the power system. It also gets data from the patient rooms through the mesh network. We were unable to get the mesh network working in time for this demo, and because of that, we have had to simulate the inputs. We were also unable to get the SPI connection between the STM32 and the ESP32 working. Decker and Mason were both working on it, but have been unable to get it working reliably. Ideally, the nurse's station would command the patient rooms to send it data, and the patient rooms would send their data through the mesh network. Once it had been transmitted and received wirelessly, the ESP32 would send the data directly to the STM32 through a wired SPI line.
The patient room control box has the ability to change between English and Spanish information on the screen. Shown in this video demo, the patient room control box is toggled between English and Spanish while going about its normal operation. There. Okay.
This is the load cell and sensor subsystem, and it's made up of two parts, the load cell and the infrared sensors. The load cell is of the hanging S type with an internal Wheatstone bridge and continuously measures the weight of the IV bag. The infrared sensors are used to measure the fluid levels at the alert and change conditions. First, the load cell circuit. There's a positive and negative excitation voltage applied to the Wheatstone bridge. The positive excitation voltage is sourced from the power subsystem and the negative from my DC to DC voltage inverter. The output signal of the load cell passes through an amplification circuit. This DC voltage is then sent to the ADC pin of the patient room STM32. This is the primary way that the fluid levels in the IV bag is measured.
Now for the actual demonstration. Decker and Ryan have successfully integrated their two subsystems and will be showing this exchange of information. To show the STM reading the data from the load cell as the weight of the IV bag varies, Ryan will apply a tension force with his hand. You can see the patient room screen initially reads 100%. As Ryan slowly decreases the tension on the load cell, you can see the values begin to drop. At 20%, the first alert condition is reached, and the screen outputs, "Nurse station has been alerted." At 5%, the more severe change bag condition is reached. The screen says, "Nurse must change IV bag now," while the buzzer sounds.
Lastly, the IR beam brake sensors. The setup is different than originally intended due to the interruption of remote learning. Our original design included a 3D printed mold that would hold the sensors at the desired location against the outside of the bag, but for today's demonstration, I will be holding the sensors by hand. The positive 3.3 volt power is simulated by the AD2. You will see as the water breaks the infrared beam, the output goes from a digital high to a digital low. This is shown in the following video demonstration.
Now to show the integration of the infrared fluid level sensors in the STM32. When the beam is broken, no audio alarm sounds. But when the fluid is no longer there, aka the beam is not broken, the audio alarm sounds. In this video, the change bag audio alarm is being demonstrated. And then
This is the flow control and monitoring subsystem. This subsystem controls the flow rate of the IV saline using a servo motor that is controlled by an STM32 to crimp the tubing, increasing or decreasing the flow rate. A keypad is used by a nurse to change the flow rate, and when the desired flow rate has been achieved, the nurse can lock the system, preventing anyone else from changing it. To unlock the system, the nurse enters a password on the same keypad used to change the flow rate.
The first demonstration shows the password functionality of the subsystem. You can see that currently the servo motor is in a locked state, since the pound and star buttons are not able to change the position of the servo. When the correct password is entered, which is 1234 in this case, the servo's position can now be changed. When the desired position is reached, pressing the 0 button locks the system again. The 0 button functions as a lock or reset button for the system, meaning that the password can only consist of the numbers 1 through 9. When locked, pressing the 0 button will restart the password attempt. The second demonstration shows the flow control working with the IV tubing. When the system is fully open, you can see that a constant stream is passing through the IV tubing. As the duty cycle is decreased, the servo arm slowly crimps the tubing, allowing less liquid to flow through the drip chamber. Something to note is that the duty cycle is either increased or decreased by 0.1% with every button push, giving the nurse fine control of the flow rate. A special bracket and arm for the servo motor were modeled and 3D printed to accomplish this flow control.
The final aspect of this subsystem is the flow monitoring. The initial plan was to use an IR beam break sensor to detect water dripping through the drip chamber, as water absorbs IR light and would have registered as the beam breaking. However, this sensor did not work, as the IR beam is not concentrated enough. This resulted in the beam never registering as broken, no matter how much or little water was passing between the sensor. To monitor the flow rate, instead, measurements were taken of the flow rate at each duty cycle of the servo motor, giving a range of values of flow rate at each position of the servo. These values would then be reported in the same way in which the values would have been reported had the IR beam break sensor worked as intended.